Good afternoon, everyone. My name is Fatima Merchant, and I'm the room host for today. Welcome. A few housekeeping notes. Please put your devices on silent to avoid any disturbance to your neighbors. All our sessions are going to be live streamed and recorded and would be available after the event. If you have any issues with your headsets, please raise your hand. Someone will come over and help you. Welcome to today's session on Agentic AI architecture patterns. This is a level 300 session. While AI has been in spotlight for many years for all the distributed systems, robotic processes, Agentic AI is giving you your time in spotlight. It's my pleasure to welcome Aaron and Andrew to the stage. Thank you. Kill it, guys.
Cool. Hi, everyone. My name's Aaron. So my background is distributed and embedded systems. And you may be asking yourself, why is a distributed and embedded systems engineer coming to talk to you about Agentic AI? It's a great question. So Agentic AI, I'm going to take you through today what agents are, software agents, the history of software agents, what's their purpose, and look at some common agents. And then my colleague Andrew is going to take you through LLM patterns and agentic workflow patterns. So what are agents, first of all? Firstly, agents are autonomous. They're mobile, they're independent. They essentially can make decisions based on their environment on their own. They are also asynchronous. Asynchronicity is a fundamental building block of agents. However, together, being asynchronous in an asynchronous environment, being able to act to real-time data, and being autonomous, being able to take action on inputs without intervention, does not make them just an agent. The fundamental building block that makes an agent is agency. What is agency? Agency is the ability to reason based on context and take action based on that reasoning in their environment. So together, an agent is autonomy, asynchronicity, and agency. Without agency, it may just be an autonomous asynchronous service or application. And what are their purpose? So Carl Hewitt's actor model, which we'll get into the history later, but the actor model paved the way for a formal understanding of agents and what were software agents and how they independently act in their environment. The purpose of an agent is to perceive its environment, to take inputs from whether it being sensory, whether it being data inputs through messaging, take those inputs, feed them into their cortex, feed them into their brain, which is the reasoning engine that uses the inputs along with their goals to create plans of action, to make decisions, to then finally take action on their environment. So an agent's purpose is to receive input from its environment, reason a reasonable action, and take action without human intervention in that environment. Now I'm going to take you through a very brief history of software agents and why a distributed systems engineer is talking to you about software agents and agentic AI as opposed to an AI/ML specialist. So in 1965 was the introduction of autonomous software entities. Don't worry, I'm not going to read out all of the names and all of the details because there's just too much to go through in half an hour. In 1973, Carl Hewitt introduced the actor model on top of the autonomous software entities, which was introduced by Selfridge, which gave way to the first independent entities acting in an environment. So it went from theory to practical application and set the actor model foundation for all future research. That future research diverged into two separate pathways. My background in control systems was in the multi-agent collaboration side of the research, which was in 1970s, I can't even see that, 1977. And in the early 1990s, the other divergent pathway of agent research was on the types of agents. So the spread of agent from very basic agents, reasoning, all the way through to very complex agent reasoning, and moved from agent reasoning into agent reason and action. And together, these two divergent pathways of research were brought together by Nwana's paper called Software Agents in 1996, which set the foundation for all future software agent development, specifically in control systems and distributed systems, for what led the future to where we are now. This was known as the study of distributed artificial intelligence. In a converging timeline, I'm sure we're all aware of Google's paper in 2017, Attention is All You Need, which was the introduction of the transformer model, which led to the creation of the GPT model, which was then released as an open source, or ChatGPT was released to the world to be able to use the GPT model through a ChatGPT application. Not an agent, it's still an application at this stage. And then after the release of ChatGPT, as everyone knows, the Gen AI hype took over, and we started developing LLMs. So after this came 2023 was the release of open source models like Minstrel, Hugging Face, Bedrock hosted, open source models hosted on Bedrock, our own models that we hosted through Bedrock, as well as other open source models. This all led to the end of 2023 into 2024, where we introduced Amazon Bedrock agents, as well as other open source agentic frameworks, and the release of Anthropic's MCP, which is the MCP model context protocol for tool interaction, or tool and resource interaction, which made agents more capable of interacting with their environment. And that brings us to now. Now we're in what we call the agentic revolution, where we've moved from autonomous software entities, where a lot of the logic that we applied in software agents was symbolic logic. A lot of it was lots and lots of rule sets. We're talking about thousands of rules to make a decision, or utilizing algorithms to understand the endpoint decision or through decision trees to get to the decision that we're making in symbolic logic. Where we've gone from there to become agentic AI, to come full circle around, is we've replaced the cortex module, or the thinking module of our agents, with LLMs. So now agentic AI is software agents utilizing LLMs to take over a lot of their cortex function. So let's take a look at the building blocks of agents. Building on top of the actor model, we have the PRA model, so that's perceive, reason, and act. To do this, first of all, obviously we need our inputs. So the perceive module, as I said before, it takes the inputs from its environment. It can be text, it can be digital streams, it could be streaming sensory data. The perception model in an agent isn't just the input of data, it is also the normalization and the processing of that data to be able to be utilized by the agent in this case, utilizing prompts with our LLMs, or in other ways of decision making that may be utilized inside the agent. From there, the cortex module has goals. So the important part of an agent is that it has some form of function. It has a goal that it needs to achieve. The cortex module takes those goals and creates a plan. It may build a top-level plan based on a single goal, or it may go and create sub-goals and sub-plans based on a higher-level goal. Based on that plan, it will then make decisions. What does it need to do to achieve its goal? And those decisions are used to take action through its action model to then interact with its environment. This could be anything from providing an output based on the analysis of data, or it could be requiring a command or some communication to a robotics platform, depending on the type of environment that it exists in. The one last thing that an agent has that is different to an application is also its memory. There is short-term and long-term memory. Short-term memory may be utilizing context caching, so prompts that the agent uses with its model may be cached for future reuse, or the speed of interacting with other inputs that are coming that require a similar decision. Or long-term memory, maybe something along the lines of reinforced learning, or it could be continuous pre-training on a model. So all of these together make up the basic building blocks of an agent. We have the perception module, which takes on the inputs. we have the Cortex module, which is our reasoning engine that takes our goals, creates a plan, and uses the available logic in our traditional sense was our static rules and our symbolic logic to form decisions, and then it feeds those decisions into our action module. What LLMs have done for us, or what generative AI has done for us, is it's allowed us to swap out that Cortex module with the context and reasoning of an LLM to take off a lot of the heavy lifting of building our reasoning engine and handing it off to a model to do it through natural language processing. Now, quickly, I will go through agent patterns before I hand over to LLM workflows and agentic workflows. So this is an example. This is not going to be all agent possibilities or all agent implementations. This is the most common agents that we are seeing. At its most basic level, the reasoning agent. Here, the triangle in the middle represents that it's doing some form of reasoning. It's not just a chat app where it's receiving an input, handing it off to the LLM and handing out the output. It will be doing some form of reasoning based on, it may do multiple queries to the LLM to form the response that it's looking for to then hand out its output. Building on top of this, I'm sure most of you are familiar with the concept of RAG. So utilizing some form of additional context. There are multiple ways of utilizing additional context, but in this way we're just going to talk about agentic RAG as the foundation or fundamental way of providing additional domain-based information from an additional source into the context or into the prompt that the agent is using to query on to query the model. In this case, it's not just directly connected to the model. The agent can utilize the domain-specific context of the RAG, so it can do search on multiple things. It may put together multiple queries for the context to send to the model, and then based on the response from that model, it may go through iterations of communicating or making decisions based on what the model is providing and what the domain-specific RAG, the domain-specific knowledge source, is providing before it gives its output. From here, we move into tool execution agents or tool use agents. A lot of people here ask me, is this MCP? This may be one implementation of MCP. However, most appropriately, the line between the agent triangle and the tool execution is MCP. That's the protocol used by the client and the server, where the server is connected to one or many tools, or you may have multiple servers connected on a one-to-one relationship with a tool. The host, the agent may be the host that contains the client, or it also may be the host that contains multiple clients. But again, what makes it an agent is its ability to query the context of the tools available to it, using the LLM, make decisions on what are the appropriate tools to take action, and then handing off an execution to the tool, receiving the tool response, and then maybe taking some additional action based on the response from that tool, or handing out the response to the initial downstream. In control systems, we're much more familiar with what we call tool servers. So all of that logic to then understand what the inbound request is and what it requires to take action on a tool is used in a platform, or tool platform, or what we call a tool server. So now the contextual understanding of tools is not handled by the agent, it's handled by the tool server, and the agent has a task understanding that it will hand off to the tool server and receive a response based on the execution of its tool. Here it will do additional reasoning and may interact multiple times with the tool server before handing back its response. I'm sure all of you have heard of computer use agents. This is a very basic look at how a computer use agent works. At the top we have the perception module is using an LLM, or in this case it would be a VLM, which is a virtual language model, which is capable of taking natural language, providing natural language understanding of what it's seeing in a snapshot. So in a computer use agent, the VLM is taking a snapshot of the computer that it's attached to. It is then using that to reason based on its knowledge or based on its goals. Those goals will come from the memory module, which can be short-term and long-term goals, or the plan that's been put forward based on the input, which could be go and create me a document on what are agents, and then will execute using the tool server based on the tools available, which could be the browser, or it could be as simple as you have access to the mouse, and now it's going to take a snapshot between where is the mouse, where do I need to move it to, and it'll move the mouse on the screen by taking snapshots and executing the mouse use tool. Based on what it needs to achieve, it will continue through cycles of VLM, LLM reasoning until it gets to the desired outcome. We then have coding agents. I'm sure most of you are familiar with QDeveloper or Copilot or Cursor. The way that they work at a very basic level is the multi-agent reasoning here, or the multi-model reasoning here may actually be one model that's attached to the IDE or is able to take context from the development environment, but it then goes through cycles of reasoning between what is the environmental context, what's the language I'm looking at, what is the IDE I'm integrated with, what is the functions that are available and open, and then taking the context, whether it be inline coding or the actual prompt required to, how do I build a React app, and then going through cycles of reasoning around this is what you need to do based on that context, handing it back over to the LLM connected to the IDE environment to then take action within the IDE. I'm going to run through this one very quickly and then jump to the most important one for my colleague. So voice agents, we're going through a cycle of text-to-speech taken from the voice or the telephonic stream, which is then done utilizing reasoning to then form a response, and then it's back from text-to-speech. Text-to-speech to then go outbound on the telephony. So this would be the basis of an agent that is sitting on a telephony stream, which could be taking queries on, basic questions on, a phone call or a phone operating platform. And finally, workflow agents. So this is the basis of an agent connected to a system where users interact with their APIs, with their applications, which are creating events in the system. Those events are subscribed by an agent. That agent, in a similar way to the tools context, has a context on agents available that it has at its disposal for workflow. It takes that context, it uses the LLM for reasoning, then the agent will decide what is the correct agent to send my workflow to, and it will start executing workflow, whether it be synchronously or asynchronously, to the workflow agents. Those workflow agents may hand a response back to the supervisor agent, or they may hand them back into the system to stimulate additional events. I will now hand over to Andrew.
Thanks, Aaron. Appreciate that. Hey, everyone. Now what we're going to do is go through some of the most common agent workflow patterns that we're observing with our customers, and then seeing how they're actually starting to resemble distributed systems. So as Aaron said before, my name's Andrew Hooker. I'm Principal Solutions Architect with Amazon Web Services. My background is across software engineering and mainly across the energy industry, but working with generative AI for the past few years. So firstly, as Aaron has covered, there are a multitude of agent types across different use cases, all right? But let's strip it right back. The basic building block of an agentic system is the model, and this is really the brain of the process, right? So it's trained on a specific set of data, but it's only to a point in time. So to provide richer responses on up-to-date information, the model can then be augmented with other data and context against its already pre-trained knowledge. So as the input, we may prepare a prompt, passing instructions or examples or memory in the following types of examples here. So we may have a retrieval process. We may want to supply up-to-date information, from a semantic search via a vector store. Or we may have tool use, as Aaron was referring to before, where we may want to hit an API to actually retrieve information or actually act upon that as well. And then finally here, we may also have memory. So maybe we want to persist state at runtime, or we actually want to then store session information long-term in a persisted state. So this in the end takes it from a stateless engine to a dynamic reasoning agent. So let's now take a look at some of the traditional application architectures which are comparable to this. So most of you have probably heard of the enrichment pattern. So at the core of this execution is the application layer here, right? So it's just a basic function. Pretend this is the agent or the model in this particular case doing the work. You then have some input in this context coming in via the client, via the API gateway, and this particular request needs to be enriched or augmented against some other form of data. Usually we have a database or something in those kinds of lines, and then provide a response. So think of that data layer here as the tools, the retrieval, or the memory in this particular case. So like this structure is both scalable and reliable, but it's static, all right? So you need, the business rules need to be explicitly coded, and context switching is particularly limited. So let's take a look at how this can be applied then building it out with agentic systems. So here we have an agent built on the Amazon Bedrock framework. And it has a model with it that it's going to be interacting with. So then we have an input via a client, and it goes directly into the Amazon Bedrock SDK. And as a part of this call, the prompt is then passed through to the agent. Then thirdly, the agent actually reviews this instruction and then dynamically looks at that via natural language processing with its own prompt and understands that it needs to route that request directly to the knowledge base, all right? Bringing that knowledge then back up through the agent and then providing that response back to the client and performing some kind of analysis reply. So the difference here is being that the agent can automatically decide the next steps or the next actions, whereas the enrichment approach utilizes a static predefined schema with fixed data sources, which are likely to provide the same responses based on the input. So this is what we like to refer to as being non-deterministic or deterministic in computer science. So what I want to do now is take you through a few of the different agent workflow patterns and the most common ones we're seeing. There's 4 particular ones here. One we've left out is the evaluator pattern, which is quite common as well. So I'll get you to take a look that up at one stage. But what I want to do here is provide you with an overview of the pattern and then provide you with a comparable distributed systems pattern that you've probably seen before, and then see what an implementation pattern looks like building this on Amazon Bedrock. So first of all, we have prompt chaining. Think of prompt chaining like a relay race. Each call passes its output to the next one, creating a step-by-step process. Better accuracy is going to be achieved through smaller, focused tasks, almost like it's a microservice with a single task. This can create options to develop quality checks along the way between those steps and provide more controlled outputs. So even with that exit process, you might want to restart that particular prompt chain, and it could be done, say, via a dead letter queue. So if we think of this as like a distributed systems pattern, this closely resembles the event choreography pattern. So obviously this is a distributed systems pattern where there is no central control and the events are submitted to corresponding content routers. Each of these routers, the event bridge in this particular case, is then moving the message to the next service, all right? So this follows that linear approach that you would have seen as a prompt chain pattern, but it's typically running as a sequential set of steps, whereas event choreography can actually run as an independent set of services concurrently and provide transaction compensation as well. So now let's have a look at what it looks like as an implementation pattern. So in agentic systems, prompt chaining resembles the choreography pattern in both structure and purpose, executing a series of reasoning steps, each building on the previous one, while preserving the context and allowing for rollback if required. So a client is going to make a call to Amazon Bedrock SDK with the intent to invoke a series of agents, but there's only ever going to be one that's only going to be invoked at this point in time from the client. So via the action group, a series of conditional steps will be taken place against the Lambda function, and then each of those particular requests are then on-routed onto each of those particular agents, chaining the prompt throughout the process. So the key difference here is prompt chaining is linear and tightly coupled, although you could do it asynchronously as well, but event choreography is distributed and loosely coupled and likely more scalable. So next up we have routing, and I like to think of routing across a few different patterns. So in the routing pattern, we have a classifier or a router agent, which is utilized as an LLM to interpret the intent or the category of the actual query. And then this on-routes that to a specialized downstream agent. So here we have input which flows through a primary router, and it might be to do something like triage requests, or we may want to like pre-process something or normalize some data before we pass it down to a different workflow, all right? This is actually really common in multi-domain use cases where you might have, or multi-domain assistance, for instance, like is this a legal request? Is it something that's like financial? Or is it something medical, for instance? Or even in the tool use. So does this go to a search, or should it go to code generation, something different? So in terms of the distributed systems pattern, we have a look at the content router. So the content router enables invocation of specific services at runtime based on those particular incoming characteristics, based on things like the payload attributes. So for instance, we may have a JSON payload which has like a type or a priority. Say it has a high priority. When it goes through the event bridge, it needs to evaluate that rule and understand that there is only a high priority for one of those particular attributes, and then route that to service A, for example. So if in agentic systems, routing is also performs dynamic task delegation, but instead of using an event bridge for rules or metadata filters, the LLM itself classifies and interprets the user's intent using the natural language understanding. Right? This result is then more flexible, it's more semantic, an adaptive form of dispatch to those end services. All right? So content routing here uses fixed rules, whereas agent routing adapts dynamically based on the context and the understanding. And I like to think that this implementation pattern can actually be solved by other ways as well. Now let's look at parallelization. So think about this pattern as a splitter process where you may need to perform a number of different tasks concurrently and then aggregate the result. So let's say we have a multimodal inference approach where we need to provide information to source reporting information or process reporting information. Then we might want to process some audio via some transcription. Or then we may want to provide a video or imaging and then assess that. Bring it all back up, aggregate that information, and then pass it back to a client. It's going to all be done by natural language in that case. So some of those use cases we could have are analysing multiple documents or perspectives, generating some diverse drafts or summaries, or accelerating throughput in batch jobs. Now in terms of that distributed systems pattern, the scatter-gather pattern is actually used to send a task to multiple services in parallel, wait for their response, and then aggregate those results in a form of consolidated output. So this pattern is actually quite common when dealing with things like federated searches or price comparison engines, aggregated data analysis, or even that multimodal inference that I was referring to before. So now in agentic systems for the implementation pattern, this closely mirrors scatter-gather by distributing some of those subtasks across multiple agents and each independently reasoning over a portion of the problem as it comes through. So this pattern is utilising a single service as an entry and exit point in this particular case, performing the request and the final of that aggregation as a result, right? This could be a long-running synchronous request or an asynchronous request, similarly shown on the scatter-gather process as well. So traditional scatter-gather is using a static path, whereas the agent parallelization adapts dynamically with intelligent task management. So now our final pattern for today. This pattern is actually common within agent workflows and typically used within coding products that make complex changes to multiple files or search tasks. So we'd have a central orchestrator agent using a model to plan, decompose and delegate these tasks to specialized worker agents, each with a specific role or domain expertise. And this then starts to form human team structures. Now this workflow is well suited for complex tasks, whereas you can't predict the subtasks that are needed at times. So whilst it's familiar to the parallelization pattern that we've shown you earlier, the key difference here is its flexibility, as subtasks aren't always predefined, but determined by the orchestrator based on the specific output. So in a traditional pattern, for distributed systems, it may resemble the event orchestration pattern, all right? So whereas there's a central coordinator, it's managing that particular workflow. And in this particular case, we have a step function where there is explicit logic built as a part of it, and it's calling these services at each particular stage. And then there may be some compensation logic as a part of it. So if we're looking at this as an orchestration pattern for agents, so each of these agents will then independently, but coordinated by an orchestrator, much like the step function, as a workflow across those Lambda functions within the previous example. So here we have a client, which is invoking this SDK, and then it's making a direct request to a supervisor agent. And this is breaking down the tasks against collaborator agents. Each of these agents have their tools, their memory, all their retrieval mechanisms, and in this case, they're actually managed via Bedrock, in this case. All these responses are then aggregated and then provided as a part of it. Now that wraps up all those particular patterns that we have, and we're starting to build out more prescriptive guidance on this, which will come in the next coming months. And there will be an evaluator pattern as a part of that. So finally, AWS provides native services to build out all of these patterns on Amazon Bedrock, covering these tools all the way from observability, security, and guardrails. But in addition to this, AWS has actually released an open source SDK, which gives you the ability to build an agent in any form of compute, like Lambda or containers or EC2, whatever your flavor is, and then integrate that directly with MCP support or other models on Bedrock, those types of things. Gives you much more flexibility as a developer. Thank you very much. Appreciate your time.
Take a selfie.